So hello everyone, thanks again for the invitation. Today I'm going to talk about hydromechanical reactivation of faults. This is work that I have done quite some time ago during my PhD. So recently there have been a lot of observations that related seismicity to industrial activities, for example, hydrocarbon exploitation, geothermal energy, or hydrofracking, groundwater, wastewater disposal, and so on. This seismicity, mainly we call it induced seismicity, and the majority of induced seismicity is linked to projects related to fluid injection. So here in this slide, I show you a few examples of earthquakes that have been suspected to have been induced by fluid injection. On the left, we have a map of the US and Canada with a few examples, and on the right, we have for Europe as well. So one of the most famous cases of induced seismicity is, of course, Oklahoma City, where in this plot, we can see the number of earthquakes having a magnitude larger than 3, the function of time. As we can see before 2008, in the blue bars, we can see that we have more or less a very low seismic activity. And starting 2009, which was associated with the year where they started to do wastewater injection in the area, we observe a very sharp increase in the seismic activity with a peak in 2015. And just for the fact, in 2014, Oklahoma recorded more than 3 times as many earthquakes as in California. Induced seismicity isn't only associated with a large increase in the seismic activity, but it can also be associated with the presence of some large earthquakes. So here I give a few examples of some big earthquakes that were suspected to be induced by fluid injection. So for example, we can talk about the Boeing earthquake in 2017 with a magnitude 5.5, which was related to geothermal projects. Besides earthquake, an increase in seismicity rate, fluid injection was also associated to the presence of a seismic slip. So here I present quickly a decameter scale injection experiment that was conducted in the south of France. The beauty of this experiment was that it was controlled, so they were able to measure pressure, injection rate, as well as measure the displacement that's being accumulated on the fault and detect any seismic events. So if we look at the figure on the left, we can see by the small circle highlighted that between 600 and 1000 seconds, we don't have any events that were detected during this time, but we still have a big amount of fault slips that was accumulated on the fault, which is mainly aseismic. So to summarize, injection-induced slip dynamics are complex. And a lot of people were interested in seeing if we can control the response of a fault to fluid injection. So in other terms, can we control what happens when we inject fluid into the earth? So I'll show you here briefly an example of an in-situ injection experiment that was conducted in Colorado in the early 1970s, where they tried to see if by controlling the reservoir pressure, they could control the number of earthquakes that they recorded during their experiments. So in this plot, the bars represent the number of earthquakes that they recorded, and the black curve represents the monthly reservoir pressure. And according to their experiment, what they observed is more or less a correlation between the two. So if we look at the start of the black curve, we can see a decrease in the reservoir pressure, which was later accompanied by a decrease in the number of earthquakes. But to better understand why does fluid injection induce seismicity or a seismic deformation, we need to go after the physics. So one of the first conceptual models that was proposed that if we inject fluid into the earth through a well, into a reservoir, if there is any permeable pathways between the reservoir and a pre-existing fault, in this case, the fluid can diffuse to a fault. will have an increase in pore pressure, which will by itself decrease the effective normal stress, and we will move the fault closer to failure. In another scenario, if we don't have any permeable pathways between the reservoir and the fault, in this case, we'll have no change in pore pressure, but we'll have a change in loading conditions, and by effect of pore elasticity, we'll change the stress state along the fault, and we can also move the fault closer to failure. So this first conceptual model is very good to understand the big picture of why fluid injection can induce seismicity, but it doesn't help us to understand the details of what we observe. So the first part of my work was really to go after these fluid injection parameters. Can we really control the seismic response of a fault if we control a little bit the injection parameters, and if yes, to what extent? And to answer this question, the first part of my work was completely a numerical modeling part in 2D, where I coupled the rate and state earthquake simulator to an injection diffusion model, which allowed me to build synthetic catalogs and look at what happens when I change the injection parameters. So, as I said, I have a 2D model of a fault. It is governed by rate and state friction. I have an heterogeneous fault. I consider a purely elastic medium. I couple this with a pressure diffusion along the fault, and all of this is in a quasi-dynamic formulation. So, as I said, I use rate and state friction law. I will not go into details that I think many of the people here already know by hand rate and state. I'll move on. So my fault is heterogeneous. Why? We were more or less inspired by the observation of seismic repeaters. Here I give an example of the San Andreas fault, where if we look at this plot, we can see that each circle represents a rupture that happened along the patch on this fault, and we can see most of the circles are collocated, which means that we have areas that are rupturing repeatedly on the fault, and we have areas where we don't have any ruptures, which might tell us that we have an heterogeneous behavior along the fault. Another motivation is the evidence of heterogeneous fault material that we can observe in the field. And finally, our last motivation was a purely numerical one. We wanted our model to be able to produce seismic activity which has statistics that we compare to real observation. So in other terms, we wanted to have a Gutenberg-Richter distribution with a coefficient B more or less close to 1, and having an heterogeneous fault helped us in this matter. So I'll show you briefly our model. So our 2D fault is composed by different patches. The different patch lengths follow the power law distribution, and we have this of C is a critical slip distance, which is proportional to the patch length. On the right, I show an example of the distribution of A, B in blue and DC in red. So we have areas which have velocity weakening behavior, and we expect them to be unstable and produce earthquakes, and we have some velocity strengthening or some barriers in our fault. I should note that the model is purely continuous fault. So each patch that we have is able to nucleate by itself. So each patch length is larger than the process zone, and we have a very small discretization cell. So our model allows us to have multiple different magnitudes emerging from our model, because each patch can nucleate by itself, and if the event is strong enough, it can pass by the barrier and nucleate along different patches as well. So as I said, we're gonna couple all of this with a pressure perturbation to make things simple for us. We decided to inject the fluid or to introduce the pressure perturbation directly on the fault at the center of the fault. So here I show you how we do it. So in this figure, we have the pressure at the injection point, so at the center of the fault. After some time of simulation, because we run the simulation before introducing any pressure perturbation, and after some time, we introduce this pressure perturbation. We impose a linear increase on the pressure, until it reaches a certain value, which we were going to define. We're going to call this Pmax, maximum pressure. Sorry. And we're going to test different values of maximum pressure going from 0.5 to 20 megapascals. To give you an idea, 20 megapascals represents a reduction of 20% of the normal stress along the fault. And as well as varying this maximum pressure, we're going to as well change the slope of the linear increase, or in other terms, we call it injection pressure rate. So how fast are we going to increase the pressure at our borehole, which is here represented by beta, the slope, and we're going to vary it from 0.01 to 10 megapascals per day. Once we introduce this pressure perturbation at the center, we allow it to diffuse along the fault. We consider a very simple linear diffusion with a constant diffusivity value. So here in this figure, I'm just showing you the different pressure profiles at different times. So it starts from the red to the gray, and finally it reaches the blue one. The blue one is when the pressure perturbation, the diffusion reaches a steady state along the fault, so it doesn't change anymore due to the boundary conditions that we impose in our model. So our governing equation, it's pretty simple. So we have on one hand the frictional stress, which is the friction coefficient multiplied by the effective normal stress. And on the other hand, we have the quasi-dynamic elastic stress, which are two terms. The first one is the elastic interactions, and the second one is the radiation damping term, because we are in quasi-dynamic formulation. As I said, we're going to use a rate and state friction, and for the state evolution, we use aging law, and we consider the additional term proposed by Klinker and Dietrich in 1992 to consider the effect of the change in normal stress on the state evolution. Finally, we couple this with the diffusion equation. So this allows us to have a set of ODEs that we're going to solve using a Runge-Kutta scheme with an adaptative time step. So in the output of our model, we're able to estimate slip rate, pressure at each point on the fault, and for each time in the seismic cycle, and we're able to build synthetic earthquake catalogs. So first, I'm going to show you the example of one simulation. So here in black, we have the seismicity rate as a function of time, and the time is normalized from the injection start. I should note that the black dashed line at the bottom, which is constant, represents the background seismicity rate. So the seismicity before we started the injection, it was mainly constant in our fault. So to look at the seismicity rate, we observe three different phases. In phase one, we have an increase until it reaches a peak. Then in phase two, it decreases. And in phase three, it is constant, and mainly it retakes the initial background seismicity value. So to understand why we have this behavior, we looked at the pore pressure along the fault. So here is the mean value, one value along the entire fault. If we just look at phase three, we see that in this phase, we have a constant value of pore pressure. So we have already reached a steady state. Maybe this constant value explains why we have as well a constant seismicity rate. But in phase one and phase two, we have a pore pressure that increase, and it doesn't explain the behavior of the seismicity rate. This is why we looked at the pore pressure rate along the fault, so the change in pore pressure. And again, we look at the mean value over the entire fault. And here, if we look at phase one, we have an increase of pore pressure rate, which is later accompanied by an increase in seismicity rate. And in phase two, we have a decrease of pore pressure rate accompanied by a decrease of seismicity rate. So basically, our first observation that we made is that the seismicity rate is temporally correlated with the pore pressure rate and not with the pore pressure itself. This led us to think a little bit about the study that was published by Langenbusch and Zobak in 2016, where they were looking at the seismicity in Oklahoma. So the green curve represents the seismicity rate, and the blue one represents the injected volume. We observe more or less a similar tendency between the two, but we have a time lag of 1 year. So in the study, what they did, they tried to simulate the pore pressure at 3 kilometer, sorry, the pore pressure rate at 3 kilometer below injection. And they plot it here in red, and more or less they observe the same thing that we do, which is a correlation between the pore pressure rate and the seismicity rate. So this was the result of one simulation. As I said, we want to explore the effect of changing the injection parameters. So to compare the different simulations, what we did is we estimated the maximum seismicity rate. So here it's S max, and we divided it by the background seismicity rate as 0. So we have a ratio S max over S0, which represents how much the seismicity is being amplified due to fluid injection. So here in this plot, on the y-axis, I have this ratio, which I just talked about, S max over S0. And the x-axis, I have the injection pressure rate, beta, and the color scale represents the maximum injection pressure, Pmax. So at first, I'm going to start with the injection pressure. Going from blue to red, we are increasing the maximum pressure. And by doing so, we are also increasing the amplification of the seismicity. So when we use a larger injection pressure, we expect to have a larger induced seismicity. Now, if you look at the other parameter, which is the injection pressure rate, beta, so as well, by increasing beta, we observe an increase in the amplification of seismicity as well. But at some point, we reach a sort of plateau. So for example, if you look at this green curve here, beyond 2 megapascals per day, we observe that the seismicity rate is constant. So we are not producing more earthquakes anymore. And if you look, for example, at this one, the red one, we have the same behavior, but we can see that the value at which the plateau is reached is not the same for the different plots. So at some point, we're changing the injection parameters, but we're not changing the seismicity rate. So to understand a bit more what's happening, we decided to look at the energy in our system. So to look at the seismic moment. So now on the right, we have in the y-axis basically the same, just the seismicity rate, but now in the x-axis, we have the seismic moment rate released. The color scale is still the same. We observe more or less a similar tendency. So at first, we have the seismicity rate that's increasing, as well as the seismic moment rate is increasing as well. But beyond a certain level, the seismic moment continues to increase, but the seismicity rate reaches a plateau. So we don't have more numerous earthquakes, but we have a seismic moment release that is larger. So we have maybe larger magnitudes that come out of our system. So we observe an important trade-off between the number of induced earthquakes and their magnitude content. To highlight this trade-off a little bit more, we try to compare our results with the analytical model proposed by Dietrich in 1994. To those who are not very familiar with this model, this is an analytical solution for the seismicity rate following stress perturbation. It's also based on latent state friction. It consists mainly of a population of identical asperities that are modeled as spring slider systems. The different asperities are close to failure, but they do not interact. So we don't have any stress transfer between the different asperities. And for this reason, we don't have any variation in earthquake magnitudes in this model. So if we have ruptures in this analytical model, we will always have the same rupture happening again and again and again. So if you look at the comparison, so the solid lines represents our model coming from the heterogeneous fault, and the dashed lines represents the results coming from the analytical solution of Dietrich's 1994 model. And as we can see, which is mainly what we expected, we don't reach a plateau in Dietrich's model. The seismicity rate always continue to increase, which is why, because we don't have any emergence of larger magnitudes in our system. So to compensate that, we have more and more earthquakes. So far, what I showed you, we have used a simplified constant diffusivity vector. However, there were many observations that showed that fault permeability or hydraulic diffusivity change during fluid injection. And here I show you an example of a study by Kappa et al. In 2018, where he shows by the different dots is the fault permeability. He shows how it's increased during the injection experiment that they conducted. So the second part of my work, where I combined lab experiments and numerical modeling, it was in 3D. The idea behind that was to go after the hydraulic diffusivity evolution and to understand what's happening. And our ultimate goal was to take this information, go back to our numerical model, put it there and see what's gonna change in our results. So I'm gonna be very brief in this section. So we conducted some lab experiments on rock samples. We had a pre-existing fault in the rock sample, which is here represented by the red ellipse. It is a so-cut fault at a 30-degree. We conducted experiment at 3 different confining pressure. We had 2 boreholes drilled at 2 opposite sides of the fault. The first one was used to inject fluid into the fault. The second one was sealed, so the fluid was trapped, but the 2 boreholes were served as well to put pressure sensors. So we have values of pressure at 2 locations on our fault. So this is what we can get from the lab experiments. In black, we have the pressure. The solid line is at the injection borehole. The dashed line is at the observation borehole. And in red, we have the cumulative displacement. And the idea was to invert this data in order to find the best diffusivity vector that can explain this data. I'm not gonna go into the details of the inversion, but I'm ready to discuss with anyone who is interested. I'm gonna directly show you some of the results. So here we have the time history of the diffusivity for one of the experiments. So we have diffusivity as a function of time. The color scale is the probability density. More or less, if we look at the general trend, we observe that the diffusivity increased by 1 order of magnitude, more or less during the injection experiment. So what's happening? We have pore pressure increase, and thus we have a reduction of effective stress. And to understand what's happening, we try to look more synthesizedly at the result of the different experiments. So here we have the 3 experiments. The color represents the different confining pressures. And the Y scale, we have the variation of the diffusivity. And on the X scale, we have the variation in the normal stress. And basically what we see, we observe more or less a clear relation between diffusivity change and effective normal stress change. So basically fluid rock interactions are complex and there are 2-way effects which we need to consider. So as I said, our goal was to have a fully coupled model. So what we did is we tried to simulate the lab experiments with our model. We tried 2 different cases. The first one, we considered a diffusivity that doesn't change, a constant one. And in the second case, we considered a diffusivity that changes with time according to our inversion. So here I show you the first one where it's constant. The diamonds represent the values from the lab. And here the black dashed curve is the numerical pressure at the observation borehole. Of course, it doesn't match the observation because we have a constant diffusivity. But if we look at the shear displacement that comes from our numerical model, you can see how much it's small compared to the values that we have in the lab. Now, if we use the inverted diffusivity history, you can see the black dashed curves more or less is a very good match to the pressures that we observe in the lab. And in this case, you can see how much the shear displacement has increased from the first case to the second one. Of course, we don't have an exact similar behavior to what we have in the lab. This is a very first attempt at doing so, but at least we can see the effect of considering an evolution diffusivity with respect to a constant one, how much it affects the shear displacement. I'm gonna stop here to conclude. As I showed you, fluid-induced slip dynamics are complex. There's still a lot that we don't know. So we still need a lot more skills in order to go a little bit beyond. And I think we still we're lacking a lot of real data processing, especially recording of some seismic slip induced by fluid injection. We still need to better understand the physical mechanism of what's happening. And beyond that, why not use the numerical tools that we have on hand to explore more complex situations? So why not go after geometrical complexity or interaction of several faults where we inject not into one specific fault, but into a medium where we can have a fault network interacting. So thank you for your attention, and I'll glad have your question in the discussion session.